Hi everybody! This video is continuing a series of videos on optical mineralogy, and today we'll be covering uniaxial materials. Last time we went through examples of how light interacts with anisotropic materials. Anisotropic materials are defined by multiple refractive indices, and as light travels through them, it is going to be split into two rays that vibrate in perpendicular directions, unless you happen to be looking down an optic axis. This splitting of light allows anisotropic materials to exhibit pleochroism in plane polarized light, and also the transmission of light under cross polarization. Let's review these phenomena with actual images of crystals. In our upper row of images, we see that when our plane polarized light is aligned with epsilon, there is only one image in the calcite, and this image is associated with the extraordinary ray. Our tourmaline displays a pleochroic end-member color, associated with epsilon. In our middle row of images, because the plane polarized light is not aligned with either omega or epsilon, the light is actually going to be split into two rays vibrating in mutually perpendicular directions. We see two images in the calcite, and the pleochroic color of the tourmaline is in between our two end members. In our bottom row of images, we see that our plane polarized light is aligned with omega, producing one image in the calcite associated with the ordinary ray, and our other pleochroic end-member color in the tourmaline. Let's drop our images of the calcite now and add some of the tourmaline under cross-polarized light to finish up our explanation. We see that when our plane polarized light is aligned with either epsilon or omega, no light is transmitted under cross-polarization. And the maximum amount of light transmitted under crossed polarizers occurs when the tourmaline is rotated 45 degrees from either epsilon or omega. This is where our plane polarized light is about equally split between our two rays. We also looked at our tourmaline down the c-axis and noted that this direction in the crystal was unique. In this direction, no matter how we rotate the crystal, we will only be seeing light associated with refractive index omega. This causes the view through the crystal to essentially behave like an isotropic substance. And this direction through the crystal is called the optic axis. So that's about what we covered in our last video. Let's now delve forward into more what makes uniaxial materials unique. So, our uniaxial materials are going to be defined by two refractive indices. Because of this, they're going to have one optic axis, which is a direction in which the material basically behaves isotropically. Thankfully, for uniaxial materials, the crystallographic orientations and the orientation of the optic axis actually aligns very nicely. The optic axis is always the C crystallographic axis for these materials. And if we can identify a material as uniaxial, that means it must belong to either the hexagonal, trigonal, or tetragonal crystal system. You know, the crystal systems in which the c-axis is always the unique axis. So if you recall back to our isotropic video, you'll remember that isotropic crystalline solids are going to be part of the isometric crystal class. That leaves biaxial materials as members of either orthorhombic, monoclinic, or triclinic crystal systems. So here's a handy chart to remember all those things. So our first cut is just determining whether or not something is anisotropic or isotropic. And now let's talk about how we can figure out uniaxial from biaxial. Let's actually start off here by going all the way back to spinel from our isotropic video to explain an important concept. We've already made some diagrams about refractive indices, but let's make one now for our spinel. Since spinel is isotropic, it's actually going to be pretty simple. It'll just be a circle with a refractive index n, which is the same refractive index no matter how you're looking through spinel. But let's say I want a three-dimensional representation of the refractive indices of spinel. This is what is known as the optical indicatrix. Right now, our two-dimensional diagram is really only representing one view through spinel. So what would a three-dimensional representation of the refractive indices of spinel look like? A sphere! So if you imagine rotating our two-dimensional image along an axis, we generate the optical indicatrix for spinel. So the way we can use this diagram is as follows. Whenever we view spinel, imagine that we're cutting a plane through the optical indicatrix of the spinel perpendicular to the direction in which we're viewing. For spinel, this ends up being kind of trivial because no matter what direction you're looking, the plane we're cutting through the optical indicatrix is always going to be a circle. And this is the same for any isotropic substance. But now that we've looked at a trivial example, let's get a bit fancier. In our tourmaline video last time, we had two different views that we looked at the tourmaline. One looking down the c-axis and another looking down the plane of the a-axes. We also illustrated views of how our refractive indices would look in either of these orientations. But now let's imagine what our three-dimensional optical indicatrix would look like. Our three-dimensional indicatrix can be generated by imagining us spinning our refractive index diagrams along the c-axis. So hopefully this makes sense to you, and now we're going to take these diagrams and use them like we did with the spinel. We already know what our views down the a-axis and the c-axis looks like, so why don't we take a view through our optical indicatrix at an oddball angle. And this is the diagram you'd end up with if we're not looking down either the a-axis or the c-axis. We see that this view generates an ellipse with axes made up of omega and what we're going to call epsilon prime. Epsilon prime is a refractive index value in between omega and true epsilon. So let's review our possible diagrams. For uniaxial minerals, we have the three following options for diagrams. We can either start out looking down the plane of the a-axis of the uniaxial mineral, in which case we'll see a diagram similar to the furthest left, where we generate an ellipse with the axes being omega and epsilon proper. If we're looking down the c-axis of our uniaxial mineral, we'll generate the rightmost figure, a circle with radius omega. Any other view through our crystal is going to generate a diagram that consists of an ellipse with axes omega and epsilon prime, the middle diagram, and the value of epsilon prime will vary between omega and epsilon depending on the orientation of our mineral. So we've got one more caveat to introduce, and that's that there are actually two flavors of uniaxial minerals, uniaxial negative and uniaxial positive. So far, all our diagrams are for uniaxial negative materials, in which epsilon is going to be less than omega. The indicatrices for these substances will be an oblate spheroid. Uniaxial positive minerals are those in which epsilon is greater than omega. The indicatrices for these materials are prolate spheroids. So let's get back to the bigger picture now that we've dug into some of these details about uniaxial materials. Basically, if we want to identify a substance, what we need to do is line up the crystallographic axes that we can identify either through crystal form or say a cleavage plane, and then the optical properties that we can view from our pleochroism and extinction and such. Here are figures that illustrate that for our tourmaline. I usually like to think of this as follows. This triangle of concepts illustrates the point. If we know any two pieces of the triangle, we can figure out the third. So let's play around with a piece of synthetic corundum now, which is a uniaxial negative material as well. Because we already know this is corundum, we're going to use its optical properties in order to figure out the crystallographic directions in our material. Our optical indicatrix here shows us how the optical properties and our crystallographic directions align. I've cut this corundum, so we'll be stuck with either one of these two views of the optical indicatrix. Either we'll be looking down the optic axis, and therefore also be looking down the c-axis of the corundum, as shown in the figure on the right, or we'll be looking down the circular section, a plane perpendicular to the optic axis which coincides with the a-axis of our crystal, as is shown in the figure on the left. You've patiently made it through all the theory, so let's go into practice. This is a piece of corundum manufactured synthetically by the Verneuil process. As such, its original shape was that of a bowl, a somewhat cylindrical solid that had been split in half. This splitting was to relieve internal stresses within the synthetic material. As such, the material we're looking at has two faces related to its original bowl form, as well as four faces that I've cut and polished. Another thing to note with this is that because of its synthetic origin, and because of this particular color, we actually have the colorant concentrated at the outer edge of this bowl. This will come into play a bit with our pleochroic colors later on. We are currently viewing the sample in plain polarized light, so let's spin it around and see if we can notice any pleochroism. So as we spin, you can notice the color become darker and more purple. Since we see pleochroism, that means this direction through the crystal is not the optic axis. And if I did a good job cutting the corundum, that means we're looking down the plane of the A-axes. This plane will have the maximum difference in refractive indices, and as such also the maximum difference in pleochroic colors. Many views through our crystal will exhibit pleochroism, but only when we're looking down the plane of the A-axes, also known as the circular section, will we see the maximum. Let's reset our sample to its original position, and let's view our sample now with crossed polarizers and see what happens as we spin. As the polarizer comes in, we see that the sample is very dark. This means our plane polarized light is aligned with either epsilon or omega. As we spin, light starts to be transmitted through the crystal. We reach our maximum brightness, and we transition back into darkness as we continue spinning. Once again, we must now be aligned with either epsilon or omega. So, let's now flip our sample onto a different viewing face and see how it looks in plane polarized light in a different direction. So as we begin to spin our sample, you'll notice that not really much of anything is happening. So we don't have any pleochroism when looking in this direction, and that means we're looking down the optic axis and the C-axis. This also means that the color we're seeing is associated with omega. So by looking down this direction in our crystal, we've managed to determine that omega is associated with the darker pleochroism end member color. This means that epsilon is associated with the lighter pleochroism end member color. This is one of the reasons why the view down the optic axis is important, since we know that we are seeing omega. So let's summarize our results of looking at the sample in plane polarized light now that we've managed to isolate which color is associated with epsilon and which is with omega. Let's continue looking down the optic axis of our sample, but now let's look with crossed polarizers. We should expect to see the sample at extinction when looking down the optic axis, because it should be behaving isotropically, but we don't quite see that here. We'll spin the sample a bit now to see how it looks as we rotate. So something very strange is going on here, and in part this is associated with the sample being made of a synthetic material. The Verneuil process results in a whole bunch of stress remaining within the corundum produced. And mechanical stress is one of the things that can make isotropic substances behave anisotropically. You'll also notice some fun red and blue colors showing up as we rotate. So now's a good time to explain a little bit more about interference colors. So anytime we see light under crossed polarizers, what we're actually seeing is what is known as an interference color. When plane polarized light enters our crystal at an angle where the light is split into a fraction associated with epsilon and a fraction associated with omega, we manage to see light being transmitted through the polarizer. Remember that omega and epsilon actually represent different refractive indices, which means that the rays of light associated with each travel through the crystal at different speeds. When the rays of light emerge from the other side of the crystal, the rays are actually out of phase. Being out of phase and forced to pass through the upper polarizer results in the generation of what is known as an interference color, which is related to the birefringence, or the difference between the refractive indices of the two rays, as well as the thickness of the material the light had to traverse. All of the samples we've been viewing are quite thick, and so what ends up happening is our interference color just looks like white light. If we had a very thin slice of a crystal that we actually knew the thickness of, the interference color could actually be used to estimate the birefringence through that view of our crystal. This is actually extremely useful for identifying unknown minerals in thin section, as an accurate birefringence measurement can be diagnostic. Without knowing the actual thickness of our sample, we can't accurately determine what our birefringence would be. But the fun colors we're seeing do appear to be maybe first-order reds and second-order blues. Given the extreme thickness of our sample, what this suggests is that there's a very slight difference in refractive indices that we're seeing. We've got another check on this that we'll look into a bit later as well. So we've now identified views looking down both the optic axis and the circular section of our synthetic corundum. By using our optical properties, we now also know where our A-axes and our C-axes are of our crystal. So we have one more view we can look along our synthetic corundum, given how I cut the sample. This should also be a view looking down the a-axes, but let's just take a look to be sure. We're doing this view second because this view is a little squirrely, since we're actually looking through that whole band of colorant concentrated at the edge of our bowl. So our colors are going to be slightly different. And it's not due to pleochroism, but due to a concentration gradient of the colorant. But here, let's spin the sample and see if it exhibits pleochroism. And as before, we start out with a lighter color, and as we spin, it gradually darkens. Now we'll reset and look at the sample under cross polarization. We learned with our other view that epsilon is the lighter color, and right now you can see we must be aligned with epsilon. And we begin to spin and the sample starts to transmit light, and eventually we align our plane polarized light with omega, and everything is dark. So now that we've looked through all the different directions we can, let's summarize our findings. We essentially have two views through the crystal that are looking along the plane of the a-axis and the circular section perpendicular to our optic axis. These exhibit pleochroism in plane polarized light and exhibit the extinction and transmission of light under cross polarizers. There's one view through our crystal that is looking along the c-axis and optic axis. This view does not exhibit pleochroism in plane polarized light, and exhibits mostly extinction under cross-polarized light. It's behaving a little strangely, due to its synthetic origin and some residual stress in the material. So let me show you now how we can identify a material as uniaxial. We're going to need to be viewing the material along an optic axis, and also under cross-polarized light. And I'm also going to have to change our focal distance a little bit here, so you'll see the crystal is further away. And what we're going to generate is what is known as an interference figure. So we need one additional thing in this view, and that's a converging lens. What I've got here is a hand lens, but any sort of unstrained glass lens will do. So this takes a bit of fiddling to get the appropriate focal distance, but when we do, you can see what is known as a uniaxial cross. Let's make a quick diagram explaining the different parts of what we're seeing here. So what our converging lens is doing is it is allowing us to gather light traveling through the crystal in all sorts of different directions. And what we see are three main different features. The melatope is the point in this interference figure where the optic axis is emerging from our crystal. Because the light here is traveling along the optic axis, under cross polarization this area should remain dark. The areas of darkness that make up the arms of the uniaxial cross are known as isogyres. These correspond with the vibrational direction of our plane polarized light, as well as the vibrational direction blocked by our upper polarizer. The circles of color that you see are what are known as isochromes. These are areas of equal difference in refractive indices between our two rays. Basically, as we move further and further away from our optic axis, the difference between epsilon prime and omega increases, resulting in rings of interference colors of progressively higher order. So when we don't really know the thickness of our sample, this isn't super useful, but say if we were looking at a thin section, we could get an idea of the difference between our refractive indices based on the number of these rings. So the important take-home message, if you can generate this type of interference figure, is that your sample is going to be uniaxial. Now, there are some caveats I should mention, in particular with this sample as well. You may have noticed that the two isogyres actually started to look like they were splitting apart, and you can kind of see that here in this video. The splitting of those isogyres is actually more of a biaxial behavior, but we'll talk about biaxial interference figures more with our next video on biaxial minerals in particular. Once again, our corundum sample is behaving a bit badly due to the stress within the sample. So I should also mention that when you're generating an interference figure, you also want to rotate the mineral itself to make sure that our interference figure is centered. So in order to do that, I reset everything and just set up a little stand for my upper polarizer. And now you get to watch me attempt to coordinate both holding a hand lens and rotating mineral at the same time. So if our mineral is uniaxial, as we rotate, it shouldn't really change from that initial figure of the uniaxial cross sort of that we're seeing here. It should basically just be that the entire time. And it is mostly that as we're rotating. It does once again behave a bit badly because I think our corundum has some residual stress within. But if we weren't looking down the optic axis exactly, as we rotated the sample, what essentially would happen is the center of that cross would start to wobble around in a circle, and then we could tell it was a bit off axis. This will also become more important when we're looking at biaxial interference figures. So now let me show you a different type of interference figure that's generated when looking down the plane of the A-axes of our corundum. This next interference figure is known as a flash figure, and it's actually really boring. So we've flipped the corundum onto a face where we're looking down the plane of the A-axes, and we'll rotate it to a 45-degree position, so we'll initially get some light transmitted through it under cross-polarization. We add in our upper polarizer, and now let's bring in the hand lens and see if anything interesting happens. And not really much of anything interesting happens. So with the flash figure, what you're supposed to do is rotate the crystal, and then what happens is it rapidly transitions from the transmission of light to extinction as diffuse isogyres sweep into the field of view. So we'll do that now, and you basically will see what I just explained. Now the flash figure isn't nearly as awesome looking as the optic axis figure, but it does tell us something important. If we correctly identify the flash figure, we know we're looking down the plane of the A-axes for our uniaxial mineral. So let's review what we learned about uniaxial materials today. Our uniaxial materials are going to have two refractive indices, and they're going to have a single optic axis because of this. Thankfully, our crystallographic orientations and our optic axis are going to align. The C-axis of our crystals are always going to be our optic axes for uniaxial materials. And the plane of the A-axes is always going to be the circular section, or the direction in which we can view the maximum difference in refractive indices. If we can identify a substance as uniaxial, we know it has to belong to either the hexagonal, trigonal, or tetragonal crystal system. Here's that summarized in a chart. We also talked about how we can subdivide uniaxial materials into two different groups, those which are uniaxial negative, where omega is greater than epsilon, and those which are uniaxial positive, where epsilon is greater than omega. We talked about how we can combine any two of three concepts in order to figure out the third. If we know the crystallography and optical properties of a material, we can identify it. If we know the optical properties and what a material is, we can figure out the crystallography. And that's exactly what we did for our sample of corundum. We talked about how we can translate the optical indicatrix for corundum into actual properties that we observe. This allowed us to determine which crystallographic directions we were looking in our sample. Pleochroism in plane polarized light and extinction and transmission in cross-polarized light meant we were looking down the A-axes of our corundum. A lack of pleochroism and mostly extinction under cross-polarized light meant we were looking down the C-axis of our corundum. Finding this optic axis also allowed us to do a new trick, which was to generate an optic axis interference figure for uniaxial materials. This requires the addition of a converging lens above our upper polarizer, and the resulting uniaxial cross interference figure is diagnostic that this material is actually uniaxial. Well, except of course for our corundum behaving a little bit squirrely due to internal stresses. So for our next and last video in this series, we're going to look at the optical properties of biaxial minerals. And of course, we've saved the most complex and convoluted for last, so make sure you have a good idea of what's going on in these previous videos before trying the last one. Alright, thanks and have a nice day.